Okay, so hello everybody. It's the CUDA Open Lab seminar, the first one, spring 2024, and it's our greatest pleasure to have Michele Coscia from that's the IT University called Cornwall.
Yeah.
Michele is a professor. We go back quite a while. We had the pleasure to sit side by side on the desk for a year at Barabasi Lab. Where one thing that sort of joined us is like I have a background in art history and archaeology, did a little bit too much computation. And I think Michele is you're a computer scientist who had a little bit too much humanities in your formation phase, coming out of PISA. And we were encouraged by your PhD advisors to work together, which we did on a thing where we analyzed co-occurrence in a large archaeological database with rule mining and network science. So we combined networks and machine learning. And the weirdest stuff about this was like the only place where we could publish something like this was a workshop at KDD, which already had a hardcore crowd doing that kind of stuff. And so that was a really, really fun time, which I remember very well. Ever since, you have been very successful. You have written sort of a kind of open source textbook on network science. You've engaged with archaeologists. What not so many people know that you have been a moderator in a huge Italian film forum. So you definitely have been ultra seasoned in humanities, cultural materials, and also contemporary culture. So it was a very great pleasure. We're looking forward to your intervention/talk on sort of what you have achieved in the last while and what you're most enthusiastic about right now. So the stage is yours, and we take the discussion from there in however way you want. So you can, we have a 2-hour time slot till 4, and whatever you want, we can do. Like if you want to take questions in between, you sway, or you say, no, I want to talk for 40 minutes, and then we talk, like whatever you want.
Thank you very much. Yeah, I'm sharing my screen. I haven't really tried my presentation. I'm gonna just do it and see how it works out. And maybe one thing that that I haven't, I don't know if I told Max, is that I actually have a funded project now doing archaeology in the Roman Empire with networks. So that is gonna start late in the fall. So let's see how that will work out. Okay, so I hope you can hear me well. Today I'm gonna talk about doing node analysis with complex networks for cultural analytics. And as Max introduced me, I am kind of like a network guy. So all of the things that I'm gonna talk to you about today is related to a new way, or like a way that I have found useful to analyze complex networks. So I just thought of having a little bit of a introductory slides to make clear that we all know what we're talking about. Although I'm pretty sure that if you guys are talking with Max and working with Max, you know what a network is, but here we are. So the idea here is that we have a structure, which is called complex networks, where we have nodes, which are some sort of entities that are connected by edges because they have some sort of relationship. Now the network that you see here is pretty much abstract. You don't know what this means, but you will see it multiple times during this presentation, and every time you will know and get to learn something new about this network, what it means to have it. But so far, let's talk in abstract terms. We have a network with entities somehow connected because they have some sort of relationship. And the idea here is that we also have attributes on these nodes. So the nodes are not just entities, and the connection that they have is not everything you know about them. You also have a bunch of other attributes that gives values to these nodes. Now, for this talk, I'm going to focus on quantitative attributes, so things that you can count or you can estimate with a number. And I'm very interested in actually having a discussion and talking on qualitative type of data. I can think about some nice ways to make qualitative attributes into quantitative ones, But rather than having like sort of generic purposes transformation, it will be interesting to talk about specific instances of how this could be helpful for other research questions that have other types of attributes, right? The fundamental question here is that how do we make sense of these attributes on the nodes? This is where probably this talks departs a little bit from other ways of interpreting network analysis, because in most of the cases where I read a paper about network analysis, people are trying to make sense of the structure itself. But here, I'm more interested in making sense of the attributes on the nodes. The structure is something that mediates these attributes and probably influence them. But it's not ultimately the most important or interesting thing. And I'm going to expand on this. So why am I doing network analysis? Well, I think that networks are very useful, and I think a lot of people agree because there are a lot of people working with networks. And I very tentatively, not super confident, but I think that I can divide the things that people do with networks in mostly 3 bins. I don't want to put anybody into a bin and confine them there, but that's more or less if I want to organize my brain about what I read about networks. I read about mostly 3 things. Like the first thing is that networks enlighten your vision of a problem. So when you represent a phenomenon with a network, somehow you can start seeing, okay, things that are connected they really do make a lot of sense. I can spend a lot of time talking about the specific connection or the specific path that there's this cluster here of things that are densely connected, and this cluster there, things that are densely connected and don't talk to each other. Yeah, I have millions of reasons why that's the case. Or it's even like, oh, there's this connection I didn't expect. So what? So even just visualizing the data is like the most basic thing that networks can do, but they do it well sometimes if you can make a proper visualization. I think this picture I like very much because you still don't know what it is, but when I start to explain to you what it is, you will figure out that, oh yeah, it makes sense, or at the very least, you can see the reason why things are happening this way, right? What are these clusters? What are these spokes? Another thing that you can do is, as I said, you can analyze the structure. So you can say, okay, well, it's not just visualization. It's not just trying to make sense of what you're seeing at a superficial level, but you can actually perform an analysis on it and try to confirm with an algorithm or with a measure or with something similar to that, that the structural property are interesting. You can calculate a lot of things about a network. Average degree, clustering coefficients, these are all the structural properties. You can do meso-level analysis. You can find communities. You can group things, group set of entities, sets of nodes, because they have something in common in the network. So you can do this sort of structural analysis that hopefully will tell you, may confirm what you already knew about the structure, or may tell you something new. You can discover things about the structure. And finally, you can run processes on your network. The idea here is that you can see, for instance, things that propagate on this network. You can see the animation because I spent so much time making the animation. Then, for instance, the classical case is like an epidemic model. You have a social network, you have people who are infected with a disease, and you know that this disease can pass through the social connection because they have connection with each other. And so things propagate. And this model is quite general, so you can actually have other things propagating, like a word to mouth when it comes to a product in marketing, or I don't know, memes can propagate through a network. So in general, this SIS model or SIR, like these epidemics models, are very popular, a very popular way of running a process in the network. With that said, like processes on the network can also be structural processes, so you can also create, delete connections of nodes. I'm not going to focus on that too much because I think that's actually pretty well understood. But I want to focus on these process things, and I want to focus on node level processes, because I think that while very interesting, things like the SIS and SIR model, these epidemiological models, they're not the full picture. There are more things that you can do than simply running an SIS model. So for this, I'm gonna give you an additional context about what this picture is. This network is actually a network of music. So the nodes in this network are bands, and they are connected if some members that played for one band also played for another band. And this has a statistically significant connection between the two bands, right? And so this is a specific focus. You can see this network is relatively small. You think that music is a little bit more than this. This is only records that have been published in Italy by Italian bands. So it's like a geographical and also temporal cut of the data, because if people didn't record their music on an actual record that got sold, then it's not in the network. So this starts at the beginning of the 20th century. And so here you can see, okay, well, but these different bands will probably play different genres. So, and this is a collaboration network. So you can say, well, these genres will propagate over time. Shared members between bands will probably influence bands to play in a similar way, or somewhat they will bring their skill sets to a different environment, and maybe they can get a convergence, so like a merging of genres. So there are these sort of dynamics that they are in a sense a contagion, but perhaps they can be described in a different way than simply a contagion. And we will see something today about this. Another thing that you can do, you can try to look at genetic relation in material culture networks. This is going to be a part of the talk of today that overlaps a little bit with the presentation I made in the conference in December. But basically the idea here is that when you do an archaeological dig, you will find material culture remains and you will find human remains. And you want to figure out how the two relate to each other. So if you find shared material culture, that implies that there is some sort of biological relationship as well. So like, can we talk about kinship groups? And finally, another example would be political opinions in social networks. This is a pretty classical case that a lot of people have worked on, and I can see that this approach that I have using these node attributes slightly differ from the literature, and I can see the power in this approach. In this particular case, the nodes are going to be people, and the connections are interaction on social media, and then their attributes are going to be the various strengths with which they subscribe to a specific ideology. Before we delve into these examples, which I think they are all very interesting, there is a lot of things to talk about them. I want to make these slides where I feel like it could be very trivial what I'm going to say, but I want to say it anyway, because maybe it's not trivial for everybody, and maybe it's important to just say it regardless of triviality. So, and it's not super trivial because at the very least in computer science, I do see these objections to the work that I'm doing quite a lot. So it's something that is interesting to think about. So there is some sort of equality or equivalence that I see sometimes expressed of the fact that a node, which is this thing that I represent as a red circle, is kind of like equals to its attributes. So in saying, I'm trying to say the same thing in different ways. Nodes and their attributes relate to the same entity, right? So a node is a representation of an entity. Those attributes are still a representation of that entity. So basically, they're just reference that point to the same thing in the real world, right? So in a sense, then at some level, nodes and their attributes are the same thing. They're just different representation of the same thing. So if we want to be even more strong, we can say that the node is the real representation of the entity in the network, and the attributes are specifying some other qualities of the nodes. And finally, what I see very common done in the literature is that ultimately we want to say something about the nodes. So, when you do community discovery in complex networks, you want to find groups of nodes. Sometimes you find groups of edges, but those are fringe cases. You want to say these nodes are part of the same coherent thing, right? So this is what I want to kind of unlearn. I'm also training myself to unlearn this. that this equivalence actually is not always true. I'm not saying it's false. There are plenty of cases in which all these things are true, but this is not the full picture. It's never the full picture. What I want to say is that noded attributes do not necessarily relate to the same entity. They are not necessarily the same thing, and the attributes are not merely specifying qualities of the node. And sometimes what we want to talk about is not the nodes themselves, but their attributes. The idea here is that the network is just defining, in my case, I'm not saying that that is always the case, but in my case, the network is defining the space in which interesting things happen. But ultimately, what I want to talk about is the interesting things and not necessarily the structure. I want to maybe know how the structure influences those things from happening, but the structure itself may be either trivial or just data that just allows me to do this analysis. But I really want to talk about the attributes. And so basically now what I'm gonna do is gonna show you 3 things or 4 things that you can use to color this thing that I just said. It's like, what does it mean to say something interesting about the node attributes rather than the node? So a few things that we can do. For instance, if you have multiple node attributes, let's say that you have 2 node attributes on your network, one thing that you may want to do is trying to figure out what is the distance between these 2 attributes. And distance on a network is usually a pretty trivial thing, right? So you have 2 nodes, the distance is very well defined as, for instance, the length of the shortest path between 2 nodes. So the number of steps you need to take in order to go from one to the other. But node attributes specify a quantitative value for all the nodes in the network. So how do you quantify the distance between these 2 attributes? It can be interesting to figure out. For instance, you see a network of 2 music genres, the distance between 2 music genres is interesting because then you can start to figure out how similar they are with respect to the bands that play them. We can also talk about the concentration of an attribute. So, okay, I have a single attribute, maybe I don't have multiple attributes. I have a single attribute, but I want to figure out whether the way it's the way the nodes take values in these attributes in the network, is it random or is the network actually meaningfully influencing the process that is behind these attributes, that whatever these attributes is recording, right? So that's a question that we could have. And again, here in this slide, I'm pretty abstract, but I'm gonna give some concrete example of why this is interesting, right? You can do clustering, right? So like once you have many attributes on your network, maybe you don't want to find classes of nodes, you want to find classes of these attributes. Again, if you use the example of the music genres, you have many genres and you can try to figure out what are genres, how do they organize in a hierarchical fashion, like what genres are more related to each other, right? And then you can also try to find temporal clusters. So this is like a sub-problem of the previous one, where you want to find classes of things, but these things is now classes of time. So like as time passes, you want to figure out where are the cutoff points? Where is this structure significantly changing? And here, what changes in a network, in a normal network analysis, you will say, oh, well, the structure have changed, the edges have changed, the node have changed. But here I'm saying like the node attributes have changed. There is a complete shift, for instance, in the genres that has been these bands have been playing, or who is being active in this network, right? Cool. And obviously there is much more. And again, I'm very eager to know how much this talk is inspiring you and things that you may want to do with your data. All right, so now let me try to be a little bit more concrete. So far I talked very, very abstract and a very, very high level. Let's try to go a little bit deeper into examples that you may find interesting. So the first thing that I said was, okay, we can find the distance between 2 attributes. And the distance between 2 attributes can be, for instance, in a social network. Here we are gonna try to figure out political polarization. So in a social network, nodes are people, okay? And the connections in this particular case, like in general, in social network, connections are social relations between these people. In the specific one that you see on the screen, this is Twitter, so it's like as a communication network, people sending tweets to each other, like retweeting or replying or mentioning each other. So connections are these sort of social relationships, and then attributes can be ideological score. So you can ask the question, how liberal are you? How conservative are you? Right? So you can say, okay, this person, based on what they write on their Twitter profile, we can say that they have like a high 80% of their content is very liberal, 10% is quite conservative. So you can give conservative and liberal scores, right? These are node attributes, right? Because you have a score for everybody. If you never write anything liberal or anything conservative, you're going to have a 0, but you still have a value. 0 is a proper value, right? So here, it should be clear now what the distinction is here, because what we are interested in talking about is the distance between liberal and conservative, right? So it's the distance between ideology, not the distance between people. Ideology lives in the head of people, but they are not people. So there are different things that are a little bit more of an abstract entity. So we are trying to figure out, okay, how do we measure the distance between these two ideologies? Because maybe we want to know which ideologies are close to each other, or how polarized a scenario is. Because if two ideologies tend to be very well separated, it means that there is no communication. So just to spell it out even more strongly, the fact that it's clear that the concept of liberalism is not a person should color what I said before, the fact that the node attributes is not a node. So these are the two, these two sentences are exactly saying the exact same thing using different terms. This is specific to this case. So it's interesting to talk about the ideologies, even though the nodes of the networks are not the ideologies, they are the people. The distance between these ideologies, which we can calculate with this node attributes distance, is an interesting concept to calculate, as I said before, because it gives us an idea of similarity between ideologies or political polarization, how much people are not talking to each other, right? Because the network mediates these opinion and their dynamics. So the idea is that people who hold a specific opinion will be influenced by their neighbors to change their opinion. They will select their neighbors because maybe they want to be exposed to different opinions, or they want to be reassured of their own opinion. So they will make different decisions on how to connect in the network. And so the opinions changes because the structure changes, and the structure changes because the opinion changes. So there are all these sort of interesting things that are happening in interplay between the networks and the node attributes. So it's interesting to ask this question, how far these two attributes are in the network. So how much effort would I need to make to go from a conservative area of the network to a liberal area of the network? If even these areas make sense, right? Here you can see that it does make sense. There is a very clear assortative mixing here, where people tend to connect with people that are have the same opinion as them. So you can expect this is a Twitter extracted from US politics, 2020 election, and as you can expect, blue indicates the liberal side, the Democrat side, and the red in the Republican conservative side. All right, so this is a slide of formula. I promise there isn't that much of that, but just to give an idea of how this thing works, because I said multiple times that I want to measure the distance between these attributes on a network. I didn't really say what this distance is, right? But actually, intuitively, you don't need to make too much effort trying to picture in your head, at the very least at a superficial level, what this may mean, because the distance that I have in mind is actually very, very similar and actually an equivalent of simply the Euclidean distance. We know that the Euclidean distance, you have 2 points in space, you draw a straight line between these 2 points in space, and the straight line is the Euclidean distance, which is an application of Pythagoras theorem. And the formula that you see here in the network, I hope you can see the pointer. The formula you can see here, it's the formula of the Euclidean distance. So it's how you calculate the P and Q are like your vectors, that the dimensional vector that have your position in space across all the dimensions that you have in your data. And this formula gives you the Euclidean distance. Although if you Google or if you go on Wikipedia and try to find the formula of the Euclidean distance, you will find something that is very different from this. Not very different, but a little bit different than this. But I wrote in this weird way because it allows me to make you realize that the Euclidean distance has something interesting in there that you can use to calculate network distances, because this I in between here is the identity matrix, which when put into a formula like this, does absolutely nothing. So if it was there or it's not there, it does also absolutely nothing. It doesn't change the result at all. But what it tells you here is that you could put something here, and this something is actually telling you something interesting about the space in which this distance is being calculated. The identity matrix, basically what it's saying is that all your dimensions of the analysis are equally important, and there is no special correlation between them. So this is the classical case, for instance, in the physical world. You have three-dimensional space, for instance, and it doesn't matter whether you're moving one step forward, one step to the left or the right, or you're jumping one step high, right? You're moving the same distance. So all the three dimensions in your analysis they have no relation to each other, and they're all equally important. But that's not always the case. And this is an observation that has been done many, many years ago. For instance, there is what I consider my favorite distance measure before I talked about network distance is the Mahalanobis distance, which is actually not complicated at all. Basically, it's just the Euclidean distance, but it says, okay, well, sometimes some dimensions are correlated. Like if you have your data points here in the scatter plot that I gave you, you have two dimensions space, but you can see that there is a clear correlation between these two variables, because when one tends to be high, the other tends to be high as well, right? And so Mahalanobis says, well, maybe then there is a preferred direction in this space. And moving through that preferred direction makes you move less than moving against that preferred direction, right? So in the figure, the Euclidean distance calculate distances like in the blue case, where all those blue circles are the points on those blue circles are equidistant to the center, which is the blue dot, right, in the Euclidean space. But in the Mahalanobis space is actually the green case. In the green case, okay, well, there is this preferred distance, and so these ellipses are also all equally distant from the green dot, but going into the preferred direction allows you to go what the Euclidean distance will consider as farther away, right? So the idea here is that we can deform the space according to our notion of what this space should be, rather than giving all the dimensions of analysis equally important. And this is the place where then I can put the network distance. So you can generalize this Euclidean distance to the case of the networks, and what I call generalized Euclidean distance. And you do that by plugging this L matrix. This is the Laplacian matrix, which is basically something that allows you to use the topology of the graph. And this matrix has all the properties that you need for a matrix to be well behaved in this kind of measure. So the result of this generalized Euclidean distance is exactly interpretable as the Euclidean distance, but now the movements are happening in a space where the network tells you the relationship between the dimensions. So basically what you have here is that you may have an arbitrary complex graph that I draw here on the top right, which tells you that, for instance, distance 1 is related to distance 2, 3, and 6. So moving across these 4 distances is moving a little bit less, let's say, because they are connected to each other. Where moving between dimensions 1 and 4, for instance, is a big movement because 1 and 4 are not connected to each other, right? So the idea is that the nodes are telling you what the dimensions of the analysis are. So in this scatter plot, the nodes will end up being the axis of this scatter plot. And then the data points that you have in the scatter plot are exactly the node attributes. So in this particular case, I specifically choose one attribute, and I say, okay, node 1 has this particular value, node 2 has this particular value, node 3 has this particular value, and so on and so forth, right? And then in this particular representation, tabular representation, the columns are the nodes, which are the dimensions of the analysis, and the rows are the different node attributes. And so the each node attribute tells you a specific position in a specific dimension for the specific value. Okay. So the idea here is that you can try now to figure out, okay, if a node attribute now is a data point, now I can calculate the distance between two data points, right? And that's what we do with the ideologies, right? So this is a very nice measure of ideological polarization in society. Here I have an example in the paper that I published on this measure. This that you are seeing here, we leave the world of Twitter and we enter the world of the US Congress. Whether that's better or worse, it's up to you to decide. But here you can see that we have a long timeline of interaction between members of the US Congress. And the network here is co-voting. So people are voting the same on bills a significant amount of time. And then this congressman has an ideological score. It's called nominate score, which is, again, numerical values of how they vote into Congress. And you can see how the networks evolve over time for each Congress. These two clusters between Democrats and Republicans tends to get more and more separated because there is less and less co-voting patterns. And also the score, the ideological score of the congressmen themselves become more and more different, more and more extreme and well separated in this distribution you can see. And at the very bottom, you can see how the distance between Republican ideologies and Democrat ideologies is evolving over time. And here lends to the hypothesis of this like growing polarization, where there is a peak in Congress 113th, and up until, let's say, Congress 98, there wasn't much, and then the things gradually evolved over time. So you can do this kind of analysis by simply saying, okay, what is the distance between two attributes? Which I think is pretty cool. The second example that I talked about.
There's a question.
Yeah, sorry.
And what is 108 Congress? Is it? Can you hear me?
Yes.
What is 108 Congress? Is it Eugenish Congress or the one where the first?
This is the American.
Yeah, but 108 is what?
Sorry, I didn't hear very well.
108. What year it is?
Yeah. Sorry, my audio is not great. So 113, I remember it being, I think it was Obama's first term. So here we are looking in this timeline at a pretty long timeline because each Congress is basically a 2-year snapshot, let's say, 3 years of activities. So you see that the current Congress, I think, is 118, which I didn't have data for. And so, but here we go back in time pretty deep. I think this could be like until around the first data point in this series could very well be the first Congress after World War II. And actually, this cutoff has been chosen not for any specific lack of data, because there is data for all Congresses. You can go back to the very first Congress. But from post-World War II, there was a little bit of a ideological difference between Democrats and Republicans. So the ideologies changed quite dramatically. For instance, if you want an example, which probably is very trivial and everybody knows about, but if you go all the way back to the Secession War in 1860, the ideology were quite almost the opposite, in the sense that the anti-slavery, more progressive and liberal, let's call it liberal, but maybe it's a very unfortunate choice of words. The more progressive, social progressive side was the Republican side. Lincoln was a Republican president, and most slave states were Democrat states. So it used to be kind of like different, at the very least, when it comes to the issue of social progressivism.
So the 108th is the first Bush Congress, right? So this is
The second Bush Congress.
the
second Bush Congress. So
Yeah, I think so.
First Bush Congress.
And then you also get like, so you get this sort of, you know, Peter Turchin would probably say there is a kind of undulation in this sort of like graph. So it's like,
well, there is some sort of, I mean, 111 is the first Obama Congress, and 115 is the first Trump Congress. So a new president gives you sort of a decline.
very interesting. Go on, sorry.
Yeah, I hope that I can get a better audio during the discussion, so I can actually be a little bit more precise in answering questions and a little bit more eloquent, also in catching them. All right. So unless there are further questions about this part, then I can move on because I'm going to change topic quite significantly.
Yeah, should we take questions regarding this? I think this. Would it make sense to take questions? I have one.
Yeah, I mean, yeah, because I'm not talking about this specific thing anymore.
Okay, so yeah, I like a lot this sort of idea. Talking about attributes is a neat way to talk about mesoscale structure and networks, right? One interesting thing is, obviously, if you are in the business of discretizing the world into nodes, which for social networks is sort of obvious, you say an individual is a node, but then if you connect an individual to an attribute, that again is a relationship. So if you want to be really snarky, you could say enriching a network, like a social network of individuals with attributes, is a little bit like a projection of a sort of like individual attribute network to an individual network that is enriched with these kind of things. So can you maybe, you know, sort of think about that a little bit, like how much your attributes by themselves are a network, like a bipartite classification network. So is that something? Do you think you could work in that way, or? You know,
yeah, this is a fantastic question. Also, I think that I consider then almost the entirety network science to be just bipartite networks in disguise. We try to ignore that as much as possible, but basically every network is at least a bipartite network. And the thing here is that sometimes this is a way to kind of like reduce or handle that kind of complexity. Because in this specific instance, the one about politics, I will say that it's probably the case in which I will take the criticism the most strongly, in the sense that yes, this could have been done maybe as a bipartite network analysis, maybe. But on the other hand, but it would be like a very odd bipartite network analysis, right? Because like if you think about it, in this particular case, you will have people on one side, okay, they may have relationship with each other, but also then you have only two ideologies, and so the other side of the bipartite network is like only two nodes, and at that point maybe the complexity really doesn't emerge here. But I think in this case I will take it. But in some cases you will have just too many of these kind of like n-partite structures. For instance, in the case of the music that I already started talking about, and it's going to be the dominant parts of the second half of the talk, it's already a bipartite network to start with, because it's a bipartite network of this person has played in this band, and then this band has played in these years. That's another n part. And then this band has played these genres, and this is another part, and so on and so forth. So you have this kind of n-partites, extremely complex things that use the complexity here starts to get a little bit overwhelming. And so this way of saying, okay, well, okay, sure, it is an n-partite network. I'm going to choose one dimension in which I can collapse this bipartite network if I want to. Also, I may not want to. I may analyze the bipartite network as it is. But then the other aspects then become the node attributes, because then that allows me to use this toolbox to figure out, to tame the complexity in a sense. Because then if you ask me to work with a tripartite or quadripartite network, yes, you can do it, but at some point the complexity is too much. And so this is one way to deal with it.
And you get around the problem of that one mode projection is a hard thing where you need to think about a lot of things, which in this case you don't need at all. It's like how you
in a sense, sorry.
Yeah, so if you project like a one mode projection, you need to take all sorts of things into account, like how you do the weight stuff and so on. But in this particular case, this is actually really straightforward, and you can do it because you preserve this sort of like bipartite structure by basically folding into this distance. Do I understand this right?
Yeah, that's actually a very good way to think about it. And yeah, I mean, I have spent a lot of time actually working on making this kind of how do you make the projection? What is the best strategy? Or making the projection first and then put the weights after, and then maybe figuring out which weights are actual genuine relationships and what are maybe spurious or maybe noise or maybe something else, right? So I worked a lot on that, and yeah, I think that these can save you that pain a little bit, and can embed the complexity in the structure. You have to make fewer decisions, because you say, well, if these nodes has this specific quantitative relationship with this specific concept, then just have the number, right? You don't need to figure out anything about whether the edges is there, what's the best way of using these weights, and so on and so forth.
Interesting. Okay. There's no other questions. Please go on. Very cool.
Okay. Thank you. All right. So now for the second thing I want to talk about, talking about how these attributes concentrate in a structure. And this is the part of the talk that has the most significant overlap with the talk that I did at the CRUDA conference. So the idea here is that we want to figure out whether this network that we observed and these attributes that is in this network, they're actually related to each other. One is sort of influencing the other, or vice versa. And this can be, this question can be formulated in such a way of saying, well, are the values of these attributes concentrated in the network, or dispersed in the network, or the two are no relationship whatsoever with each other? And so here we are talking about a network in an archaeological setting. So we are doing this material culture network. So the idea here is that, okay, we have this excavation site, which has a lot of buildings, and you see a picture representation here and there. And you will find things in these buildings. So you will find a mirror, for instance. And maybe you'll find same type of mirror in a different building. And now you have established a relationship between these two buildings. And again, this is a bipartite network, right? It's a building artifact kind of bipartite network, right? But then you find other things in these buildings, right? So you find human remains. And so now you are starting to ask yourself, okay, are the relationship between different classes of bipartite networks actually meaningful? So in this particular case, we decide to project on the material culture part of the network. So we want to have a network where the nodes are the buildings, and the connection is a significant amount of shared material culture between these two buildings. And the shared material culture gives you the edge weight, right? Obviously, you find a lot of this relationship, but you have some buildings that you can find more things, and some buildings you can find fewer things. And these may not be a genuine difference, because this is archaeology, is the literal definition of survivorship bias. So you only have what you can find. You only have what survived for all these thousands of years. So you need to try to figure out, use some statistics to figure out if these relationships between shared material culture are actually statistically significant. And so you have to go through this process of projecting the bipartite network and figuring out what are the most reasonable way of finding these edge weights and finding the ones that are statistically significant. So just to sum up what this network structure is, we have, as I said, buildings are nodes. The node size is the number of artifacts, so you can immediately see that some buildings are just bigger. They have more stuff. Building 1, building 77, they're very big. The edge size here is the number of shared things that you have between them, and the color is the significance. And you can see that sometimes you may have a lot of things that are not as significant as fewer things. The connection, for instance, between building 1 and building 17 is pretty thick, because we find a lot of things in common between these two buildings. But it's not particularly dark. I mean, everything you see in the picture is statistically significant, but the statistical strength of this connection is not as big as, let's say, the relationship between building 75 and building 58. We found fewer common things between these two buildings, but given that these buildings are actually have much fewer things themselves, then this connection ends up being more statistically significant. Then there is this other part of the network, this tripartite network, if you may, because you not only find material culture in buildings, this specific culture, which is a site in Turkey, Çatalhöyük. The culture was at the time and in that place was to bury their dead in the foundation of a new building. So when archaeologists excavate the remains, they will find human remains with the material culture that they find in the same building. So above there is the material culture, and beneath there is a grave. And so the idea is that now asking, what can we do with this? Well, with the burials, you can do DNA sequencing. So you can figure out who is related to whom in the various buildings. So you have sort of another way of connecting a building with what you can call a kinship group, a specific set of people that have relationships, biological relationships. And here by biological relationships, I mean first, second, or third degrees biological relations. So first degree will be siblings or mother or child. Second degree will be one removed, so you have cousins, and so on. And so we can do up until the third degree. And so the idea now is that you can consider this in one way as the node attribute.
May I ask a question to clarify?
Yes.
May I ask a question to clarify? Basically, my question is just to clarify, is what, for example, nephew and uncle is second degree, or is it as 1.5 degree? Because I mean, it seems like your degrees are actually double the possibility that for cousins it is 2 to 4 steps along the family tree.
You can actually see it. So there's parents, is
yeah.
First degree siblings, second degree is cousins, and so on.
Once again, if it is an uncle and nephew, what degree is it, and why?
Well, I mean, this I will have to ask really the biology. But as far as I can remember, I want to say is a third degree, right? Because, but then I think maybe the best way to think about this, as far as I understand, but I may say something incorrect, could be simply looking at the amount of shared genes that you have, right? A first degree relationship, as far as I can tell, you are expected to share half of the genes, right? So from your parents or from your siblings, right? Unless you are identical twins, obviously. In that case, it's like sort of a 0 degree relationship. A second degree relationship, as far as I understand, could be 25%, right? So it could be like you're expected to share 25% with your uncles, but not with your cousins. So the cousins at this point, using this definition, would be actually a third degree relationship. So a nephew uncle will be a third degree relationship. But again, don't quote me on that. I know that this is recorded and it's going to be put in the internet. So I may have just made a fool out of myself, but that's my understanding.
Okay, thank you.
Okay, I hope.
The network C, the lowest network on the figures, and if you look at them back and forth, you get a very clear idea. But people can jump back and they can pause. Like you don't need to, like, go on.
Okay. All right. So now that you have this additional part of your network, then you can decide to use it as the node attributes of the projection that you just made. So in this particular case, the material culture network is the projection that we made before. So buildings connected because they share artifacts. But now the node attributes is how many people from this specific kinship group I found in this specific building. And so here you can see one from one of the kinship group that we actually have in the data, where vast majority of them are buried in building 1, and then a few of them are buried in other different buildings. And so another question that you can ask, since we are talking about concentration of the attributes, is that, is this distribution random? So the fact that you see this number of people buried in these specific nodes, in these specific quantities, is this what you would expect if people in this culture will bury people randomly without thinking about the material culture, so thinking about the sort of other relationships that they may have, or instead if these two things are related to each other, right? And I'm sure that there are tens of different ways to do this, but I think that the concentration on the attribute to me makes a lot of sense, because if you can see that all the people are occupying a specific sector of the network, is a very intuitive way to tell, that tells me, okay, this is concentrated rather than dispersed, right? And so what we do is that we work with this concept of network variance. And I think that's the most intuitive way I have. I don't have a slide really to explain what this network variance is, but the most intuitive ways you can think about it as sort of a physical way. You can think about the concept of physical entropy, where if all your, let's say, gas particle in a room are concentrated in a specific spot, that is very unlikely thing to happen. It's very concentrated because you will expect these things to scatter randomly in the room. And this is basically the same thing. You have your room is this very complex space defined in material culture, and where these bodies are buried is how you disperse these particles in this very complex room. I think this is probably the most reductionist thing I ever said in my life. I hope that I will not be judged by that. Okay, so the bottom line of this work, which I don't dedicate too much time to it because I explained a lot of it during the presentation at the conference, is that actually we see that these families are absolutely not buried at random. They are more concentrated in this network of material culture than you would expect from a null model. So the null model, we can build a null model, we can take these people and pretend that we buried completely at random without looking at the material culture network. We extract buildings in which to bury them completely at random. And then we can calculate this sort of variance, this sort of concentration measure. And we can see that here, you can see in the plot where the observed values that we have is the green vertical line. And then the red line tells you the distribution that we obtain from the null model. And on the left, the figure A is when we only consider second-degree relationships, and figure B is when we only consider third-degree relationships. There is no picture for the first-degree relationship because we don't have enough of them. And here you can see that the result for the second-degree relationship is very strong. It's almost impossible for a null model to reproduce what we are observing. While the result for the third-degree relationships is still on the edge of statistical significance, but there is quite a big chunk of null models that can reproduce this kind of concentration, which is interesting, right? Because as we just discussed, maybe not as precise terms as I should have, but second-degree relationships are stronger, are tighter than third-degree relationships. And so it also makes sense that we find a tighter relationships when it comes to the burial. So yeah, this is one kind of things that you can do when you only have, let's say, one attribute, and you want to understand how much this attribute concentrates in the network. And in this specific case, will argue that this trick of considering these attributes as sort of another bipartite network in disguise may run into more difficulties, right? Because if you only have one attribute, so which is the number of people that are buried from this specific family on the building, then you have a bipartite structure where on one side of the bipartite, one type of node, let's say, is only one node, and it's connected with a bunch of other nodes in the other side of the network. So it makes it very tricky to do this with a bipartite network. Not that you have to do it with a bipartite network in this case, but this shows also a little bit of versatility of the measure.
Can I ask a question?
Of course.
Okay, if you go back one slide.
Yep.
So now here the colors, like, so I think I understand what you were saying, but this particular figure, what is the red color of these nodes? Is it like the concentration of one family, or how should we understand this?
Yes.
Okay.
So basically a single family.
And that means for every family you would be able to produce such a picture, right? So the underlying network structure, the
yes,
colors
absolutely,
of the
yes.
links,
So in that case, you can have a
would stay the same, but the red dots would have different concentrations. So now there is a kind of, there's like 4, 2, 1. Like, I'm a qualitative researcher. This smells like if I would have 100,000 people, there would be a power law. But so if you have many families, are they concentrated like this? Is there a cluster, a smaller cluster in the dot? Like this is a very suspicious kind of thing. So this seems like a mixture of sort of these kind of, the question is like for families, can you build some kind of like summary statistic, so to say, for all families taken together and how they're covering the network then? Or do we just have one family?
Yeah, I mean, you can do that. Now, there are a few there are a few things that I have to say, and one of those is that we don't have that many families, because, for instance, we have at the risk of non-trivial size and non-trivial distribution of the network. Because if the same family is all buried in the same nodes, trivially this is going to be concentrated in the network, but it's not very interesting because they just happens to be there. So we only have one family on non-trivial size and non-trivial distribution of second degree, while we have 3 families of third degree that are non-trivial. Also, I should point out, this is maybe not super close to addressing your question, but I've been scolded multiple times by my archaeologist colleague because I used the term family and I shouldn't, because family comes with a lot of things attached to it. These are like biologically related groups. They're not necessarily families. And specifically, the one that you're seeing in the picture, being one of these third degree biological relationship groups, it could very well be that these multiple families that you see spread out in different parts of the network, but they just happen to be all connected in this third degree sense, right?
So let me give you an example. Is there a family where B77 is dark red and B52 is mid red? So this, like basically, if you can take your model that you explained to us, and then even on a qualitative level, you can make not forecasts or predictions, but at least anticipations, where you could, where imagine you're the archaeologist excavating B77, which may cost in summer and smells like a latrine that's warmed up and wet again, right? Because there's graves and stuff. So you do that kind of stuff, and then you ask your boss, what kind of things should you excavate next in terms of human remains? You already know the cultural objects because they're in the layer above. Wouldn't it be interesting to do B52 next? See what I mean? So there's this kind of like archaeological decisions that follow from your model, which may be really interesting. Same thing is true for B65 in the upper left corner, is really central and statistically related to B58, B56, and B44 is that a similar motive as B1? Like is B65 dark red the center of one family and the other one satellites of that? And so that is sort of like, you know, basically you can build these kind of qualitative hypotheses from your sort of mathematical model, even though you have these really low numbers. And then now my question is, do these things pan out to be true? Or what we often see in quantitative archaeology, they don't pan out at all, and it all looks completely different. So that is my question, basically.
Okay, so my expectation to the answer to this question is that yes, I think that you can do this, because basically we see that, for instance, now moving away from this slide 1 second and coming back to this one, since I told you that we have multiple families in the third degree level, and I said family again, I have to put a coin in the swear jar. So this value of the observation, this vertical green line that you see, is actually an aggregation measure, right? So it tells you across all the families what is the variance that we expect, and that's what also the null model does, right? So so yeah, you can aggregate and try to say, okay, well, as a group of family, do they concentrate more than average, right? Because it's not specific to one family. It's not that one family concentrates and the other doesn't. So you can build a theoretical expectation saying that, okay, if you find a family in B1, should you excavate B3? The answer is yes, you should do that. Now, is this true? Like, can you actually verify this? We haven't done this yet because, as you mentioned, excavating a building is kind of like a difficult process and not the fastest thing in the world. But I know that in this site, there are some buildings that have been excavated, but they are not in this network because they haven't done work with the biology, I think, yet. So there is the famous building, at least for me, building 166, which sometimes I find in the data and sometimes I don't, and I always call my co-author in very worried tone about this building. So the idea is that, can we build some expectation about this building 166, about what is the sort of stuff that we are going to find inside it? I can build that expectation, and then they will excavate, and then they will obviously prove me wrong. But at the very least, I would have tried. So you can try to do that. And then the other thing about this is that this Çatalhöyük is one site in Turkey, but there are some sister sites in Turkey. There are other like 3 sites, I think, where work of excavation is being done, and so we can just try to. And the culture was very similar. We're inhabited at the same period of time, so we can actually start saying, okay, well, maybe we can try to use this as a natural experiment and try to figure out whether this information that we gather here will help us gather information in the other side.
Yeah.
Question.
May I ask one? I guess it's time to ask questions about this part now, yes? My question basically is about your null model. Basically, as you mentioned when you just talked, it seems reasonable to expect that people from the same family are buried in the very same building. Yes, so having a dark red spot somewhere is not surprising. So my question is whether your null model allows for that. So is it just distributing on all burials at random, or distributing it clusterized but randomly positioning clusters? You see what I mean?
Yes. So I don't know if this is exact. Let me see. Like, the thing that we did was that saying, okay, let's go back here. Building 1, for instance, it's a very big building. We found a lot of material culture and also a lot of remains. It's a very important building. And the idea is that in the null model, we take this into account. So we say, okay, we are burying people randomly, but not uniformly at random. It's not that we just pick a building at random. We pick at random, but it's weighted by how many remains we found in the building. Yeah, so we use that in the building. I think this is similar to a question that I actually got during the conference. I say, okay, well, can we actually make a more sophisticated null model where we can try to build some sort of expectation of like where will, like, if I extract a specific building at the beginning, like I make the first burial in building 1, let's say. Now, this building 1 now start becoming more likely to extract in the future because I just picked it as the building of my family, right? I think this is a little bit closer maybe to what you were meaning. You tell me if I'm wrong. So we haven't done that. We only use the relative popularity of the buildings as part of the null model. But I think this is interesting because I wouldn't know how to make a null model that is fair enough, but it's not also trivial that is gonna just reproduce only the data that we observe rather than actually being a null model.
Yeah, because it feels like there are two things going on here. One is that people tend to live. I mean, close relatives tend to live in the very same building, and it is something which is beyond your problem of relations between buildings. And then on top of that, these family groups tend to cluster on the network. And your null model is sort of discarding both of these things, so to speak. And therefore, for example, if you say that you have a kinship group which is concentrated in one building, it will trivially say if you do this formally the same procedure with the same null model, it will be very far to the left, but it says nothing to answer your question about whether buildings are related. Yes, so that is a little bit worrying me, but yes, it is not immediately clear how to construct the null model, but it is an interesting question. I will try to maybe.
I think it's a very interesting question.
Okay, go on. Thank you very much.
Thank you.
I think it's very interesting. I have one last thing to say about this, which is like we also tried to just make this into a relationship between the nodes in the network, right? So the idea would be, okay, we discard the number of people who have been buried in a building. We just know that this family has selected this building. So it's a 1-0. Because at that point, we are only interested in multi-buildings families, right? And see whether when a family, quote unquote, chooses another building to bury their dead in, is this choice related to the material culture? So at that point, you discard the number of people buried in a specific building, and you only take it as a 0-1 attribute. Does that also concentrate in the network? I don't quite remember. I know that I did this, but I don't quite remember exactly how it worked out. But I can take a look at that. But I see what you mean. I think this suggestion for the null model, I think it will be interesting to try to make the null model a little bit more sophisticated and say, well, if the family chooses this building first, if there's no family chooses the building first, maybe then that building gets a little bit more likely to put things in there. I think that maybe is a fair null model than just taking the relative popularity of the building itself. So I'm gonna look into this. Thank you. Okay, unless there are more questions, then I will move on to the third thing, which is learning attribute classes. So the idea here is that doing classical data clustering. So when you're doing data clustering, you need basically the idea is that you have a lot of data points, and you want to find the classes of these data points from the data itself. And how this is normally done is that you need a distance function. So if you assume that the points you see in the screen right now are all data points, well, there are some quote unquote natural clusters here because the distance between these 2 points in this 2D plane led me to think that there are 3 classes here of 3 things that go together. And so by systematically analyzing all these pairwise distances between your observation, you can find these classes, right? And in the first part of the talk, I just define for you a distance function of networks. I say, well, I mean, if you have 2 attributes on the network, we can calculate the distance between them. So it seems natural to say, well, if we were able to deploy this systematically, then we can try to find clusters, because suppose that we have tons of attributes. then you have hundreds of attributes. Then you can say, okay, well, if I systematically calculate the distance between all the pairs of these attributes, then I can try to find the clusters of these attributes. These attributes are related to each other in the way they distribute on the network. And so the very short question of doing this, so there isn't much math here, because basically you're simply just applying the generalized Euclidean distance that I explained before. The idea here is that by itself, if you just do that, actually it doesn't work that well. So here you have a lot of boxes, and I apologize for the amount of colors and confusions here, but I'm going to direct your attention to the fact that the distance measure that I discussed about in the first half of this presentation is the blue line, and the gray line here is the baseline. So just doing the clustering with an Euclidean distance, because you can calculate the Euclidean distance between node attributes. They're just vectors of numbers, right? So you can calculate the Euclidean distance with them. And so on the y-axis, you have a quality function of how well you can recover this sort of gold standard if you believe in that, right? And you can see that this approach that I explained to you is actually not that good. It seems that the network is not doing much. These are 3 different data sets, by the way. And the solution, like, I was very disappointed when I saw this result, but the solution that I found is that actually you can synergize this sort of like Euclidean distance on networks with other ways of analyzing data. Specifically, this red box here that you can see performing really well in 2 of the networks that I use them, and is the distance measure that I use, but not to find the clusters. The distance measure is used to define the space in which a dimensionality reduction techniques happen. Here I use TSNE because it was the easiest one for me to use. I know that there are better choices or different choices that you can make, but that was not the important part. The important part is that the distance measure that I have can just provide to the dimensionality reduction the shape of the space in which these things needs to happen. The dimensionality reduction needs to happen. And then after you do the dimensionality reduction, then you can find the clusters. So, and this dimensionality reduction happens embedding, incorporating the information from the network into the numerical vectors that you gather.
Is that,
and in one case,
can I ask a question?
Yeah. Yes.
Could that be because if you look at higher dimensions, you basically your Euclidean distance at some point, basically that's the reason a lot of people use cosine distance, right? Because at some point the actual distance doesn't play a role anymore because it's all angles, because every point is sort of close to every other point in high dimensions. While if you do a dimensionality reduction and you have 2 or 3 dimensions, then a Euclidean distance really makes a lot of sense.
Absolutely, yes. This is well known as the curse of dimensionality, and in networks this is also particularly problematic because normally the networks you're going to end up analyzing as usually tons of nodes, right? Because if you have a network of like 10 nodes, why are you having a network after all, right? You can analyze it kind of like more easily with less sophisticated techniques, right? So your network is usually going to be big in terms of number of dimensions that clustering algorithms are used to get. And so the more dimension you have, the more likely is that the points are end up being basically in the same place, right? And so the idea here is that, yeah, the dimensionality reduction provides that service to allow you to separate the clusters well. And basically where the edge of doing that, being aware of the network versus doing that without being aware of the network, is the difference between the red box that you can see here and the green box. The green box does the dimensionality reduction, but using an Euclidean space. And you can see that in some cases you don't get much, but in some cases you actually get a lot. And these, by the way, that you just said, Max, is part of my last slides, or like second to last slide, because it's part of the things that I want to, where I want to go from here. Because now I have this generalized Euclidean and I use the network. That's great. That's fantastic. Sometimes it's extremely useful. But as you say, sometimes it isn't. And so I really want to make a cosine similarity or cosine distance on networks. So like, can I do that using the network topology and taking that into account? Maybe, maybe not. But that's a question that I have for the future. So thank you for pointing that out. The other thing that I want to say in this slide is that that's not always the best thing. Sometimes you need to add a little bit more complexity. So in the plot in the middle, you can see that the red box is actually not that great, but there is this mystery orange box that instead is the best performing one. And in this case, I added another component to the pipeline, which is a graph autoencoder. And basically, in a nutshell, what this is doing is saying, making an assumption about noise in the network, about errors in the network. The idea is that perhaps these node attributes, there is a little bit of random fluctuations in this, and you want to clean the noise before you actually do the clustering, because then you're going to get better separated clusters. So the graph autoencoder wants to clean this noise, and the way it does it is that it passes these node values through the networks into first an encoder and then a decoder. So in the end, you end up with the same attributes as before, but you smoothed out the noise by looking at the neighbors of the nodes you were looking at. And so like this is a very strong assumption.
It's like a Gaussian blur on the network, basically.
Yes.
Okay.
I mean, obviously, it depends on which specific autoencoder operator you're using, but
sure,
for the purposes of this talk, you can thinking about a Gaussian. And this comes with a very strong assumption, right? It comes with the assumption that if you want to smooth out the noise, this noise is kind of like correlated in the structure, and so looking at your neighbors will help you reconstruct the original signal. If that assumption is wrong, so it's not maintained, you're actually damaging the performance. In fact, you can see from the plots, I think it's on the, here, you can see that all these values that are close to 0, that are actually worse than the baseline, because the baseline is actually here. So it's worse than doing just Euclidean distance. It's because the graph autoencoder is trying to smooth out some noise with a completely wrong assumption, and it just basically end up destroying the signal rather than destroying the noise.
Can you explain?
So it's a powerful tool. Sorry?
Yeah, can you explain the difference between the 3 plots at the bottom? So this is 3 different sets of networks?
Yes.
Okay.
So
what exactly is AMI? What is on the vertical? I understand that it is better to have larger value, but what is it?
Okay. What's AMI?
Okay, let me. Okay, let me unpack all the questions at once. So, okay, these are 3 networks, 3 different networks. One is a network of products that can be exported by countries in the world trade. So the products are related to each other because the same countries export them. And so we are trying to find clusters of products here. And so that, there is the world trade networks, and then these products are the things that are exported by the countries, right? And so AMI is a mutual information measure. It tells you how much the classes that you infer from your clustering align with the classes that you already have in your data. So in the case of products, we already have classifications of products. So we are trying to figure out whether this clustering that we are making of products as node attributes in the trade network conform to the classes that we already gave to the product. So, you have cars, you have planes, you have bananas, and so on and so forth, right? So the more AMI you have, the more aligned your clusters are with the classifications of the product that you have. So I think this is the network on the left. The network in the middle is politics networks. It's a network of donors. So the nodes in this network are donors that are donating money to politicians. The donors are connected if they have a social relationship. They're either related to each other or they sit in the same companies. They are part of the boards of the same companies. And then they donate to politicians. And so the politician is the node attributes, because each politician will receive a certain amount of dollars from each of the donors. And so it's a numerical attribute, right? And the idea here is that I want to find clusters that conform to the party the politician belongs to. Again, here we are talking about the US politics. And so the idea here is that you can actually find out which party somebody belongs to, depending on where in the social network of rich people they get their money from to get elected. And so here the clusters are trying, the high AMI means that I can sort politicians into clusters that are very homogeneous. I put together all Republicans with Republicans and all Democrats with Democrats. The right plot instead is a network from an amusement park. Is the Tivoli amusement park here in Denmark. And in this network, the nodes are the rides. So you have a roller coaster or whatever. And they're connected if the people ride on the same ride. So a person has a ticket, they check in the ride, and so you connect rides because they have the same people go on them. And then you know that these people hold specific passes. So there is a regular pass, a kid's pass, or an elderly pass, and so on and so forth. And so the idea here is that the class of the tickets, and then you'll try to reconstruct that class of the tickets with a cluster that you find in the data. Yeah, so these are like just to see that there are many different things that you can apply this measure to: macroeconomics for trade, political science, and then simply marketing, like because you can figure out that maybe you have two passes that are too similar, they end up in the same cluster, you may want to merge them in the same pass. Or maybe you can find different clusters that don't conform to any cluster, and maybe it's a new offering that you could offer to your customers.
So
yeah, I didn't go in depth to explain these networks because they are not very cultural analytics. I thought.
Can I ask a question though? So the product space network, right, is notoriously has product categories that are quite overlapping, particularly in the textile industry, sort of, right? So there's a really interesting thing that there is there would be some kind of, obviously, if you can do trousers, you also can do jackets as a country, right? So these two things, in some sense, ideally, you would be able with your measure to sort of make suggestions of which kind of categories to collapse. You see what I mean? Where you could say, oh, you know, dear United Nations, here you got 500 product categories, but actually you could forget about 100 of them because they actually should be merged and there's really 400. While there is this one thing you should split. Obviously, we'll never get that out of network analysis. But so one of the interesting things is it's almost like if your measure sort of allows you to reproduce the situation with high AMI, it would fall into the same fallacy as the original creators of the classification. So in other words, there is a kind of catch-22 going on between optimal design of the original classification system and optimal recognition of a classification system. So can you, or did you ever think about your method, you know, maybe by choice of, like, similarly, should I use the noise reduction or not, by choosing the right method where you say, oh, actually, you know, we should arrive at a certain value using the following combination of measurements if there is categories to be merged, basically, if that makes sense. Do you see what I mean? So
yeah. I
think
that's an interesting question. I mean,
the writing on a product categorization was designed in the 1960s or 50s, which is a sort of weird thing, right? Yeah.
Yeah, no, I mean, yeah, there is a lot of things to unpack here. So the first thing that I will say is that I will immediately think of finding AMI too high as inherently suspicious. So I will never consider that a success. I will also want to, at some level, having a relatively high AMI, because what I will think is that, sure, these categories may be questionable, but surely there was some sense in them. So the idea is that I get a non-zero AMI because I can capture the sense that was in there, and maybe I can provide some new sense. So that will be my my main thing to say if I want to be extremely defensive. But I think your comment is more interesting than that, and is probably a wide open research question here. Is that, okay, wait a second, I'm going to find some clusters using this measure, but how much can I tell whether these clusters are just because I have to find clusters, and so I say the algorithm find me 10 clusters, and the algorithm is going to do their darnest to give me 10 clusters, right? But how much I can tell, hey, there are no clusters to be found here, and can I use this measure to quantify and say beyond a certain amount, I can say, well, these things are kind of like well defined, and so kind of I can kind of talk about actual clusters here versus below certain values. Say, okay, this is an impossible mess. I think this will be very interesting. I have not thought about this line of research yet, so I will be completely honest with you. But I think there is some value. I mean, I'm pretty sure there are some approaches in the wider data clustering communities that can do that. For instance, dbScan is an algorithm that is very happy to say there are no clusters here. But it doesn't really tell you there are no clusters because you specify the parameters wrong versus there are no clusters here because there aren't clusters. So yeah, it's I will have to learn a little bit more about data clustering to evolve this work into that direction, but I think it's super interesting.
Mm-hmm. I mean, there's a you know, it's one interesting thing, like there's a meta observation about our conversation here. So we're sort of nerding off about sociocultural systems, which traditionally is the domain of the humanities, while at the same time quite hardcorely thinking about network topology and structure and dynamics and like all that kind of stuff. So one of the interesting things is that this is super important as we need to think about not only like what we're talking about, but also how good our thoughts about what we're talking about are, even if we're, for example, just humanists or just computer scientists. Like just not like meaning small, but like focusing on one mode of thinking. And one classic category is like, if you think about, you know, how many analyses actually discretize the world into countries, how many studies discretize the world into some weird sort of like subset of discrete, pseudo-discrete ethnicities, how many studies sort of like do things like categorize the world into genders, into disciplines, and like all these kind of things. And like what you're doing here gives a contribution to that, where you can actually think about sort of the discreteness of these categories. But now here's an interesting thing. You're not doing the classic thing of like, oh, here's the 2 categories in a confusion matrix, or here's the 10 categories in a confusion matrix. But it becomes clear that the way of looking at stuff determines how many clusters you see. And that is a really, really uncanny thing, because all of a sudden you have to work in a triangle, right? It's not just clusters versus overlap, like, you know, sort of modularity versus confusion, but it's also the kind of algorithms determine of what you see. And that is a really interesting thing, because that's the same uncanny situation we are as a society. If we sort of look at the world with preconceived notions, preconceived categories, what you see is categories. And, you know, you make up your own boundaries between things that may not have a boundary, but are a gradient, or vice versa. And I think that is a really, really interesting thing to sort of like do more research in, and sort of like unpack and make more clear in the next 5 to 10 years, I think, because this is very clearly something that is super, super interesting, but we're very much in the stage of like, you know, you're not going down to the university hall and in a lunch break sort of like enthusing 500 people by what you're doing here. It's too complicated still, right, isn't it?
Yeah, no, absolutely. I think that I have one thing to say about this, which is that this is probably the most computer scientist slide, because this is the exercise here was actually not to say anything interesting about any of these networks. It was just to calm down the computer science and say, hey, well, this thing actually can reproduce this sort of quote unquote ground truth, which is not ground truth at all, as you were mentioning. But this method is just not spitting random things. But the thing that I want to really focus on is something that I hope is a little bit closer to the sentiment that you just expressed, which is actually to talk about the music network that I teased at the beginning of the presentation. So I will go on with this and see, and let's see if we can get another point where we can develop the discussion a little bit. So the idea here that we are doing, the way this thing works, is that we are just calculating, as I said, the pairwise network distance between these attributes. And then we use these distances to give TSNE or whatever dimensionality reduction technique you have, the shape of the space. And then, you know, we can cluster the network aware embedding that TSNE has reduced to a few dimensions, or we cannot, and we can just visualize them and see if they enlighten us in some way. In this particular case, I decided to cluster them, but you don't have to, right? And in fact, I'm going to actually try to toe the line between clustering or not them.
I'm sorry, can you elaborate a little bit on what use these distances to give TSNE the shape of space actually means? So
Yeah.
what technically is behind this?
Yeah, I'm not going to be extremely detailed, but basically what happens is that TSNE in general is an algorithm that's is specifically for reducing dimensions, right? So you have data that has n dimensions, let's say, and you want usually to reduce this to 3 or 2 dimensions, because then you can plot it, right? So in order to be able to do this, TSNE needs to know what the distance is between the observations, because then it can systematically throw away dimensions or reduce dimensions to something more salient until you have only the 2 most salient dimensions that you have in the data, which are not necessarily the dimensions that were already there. They can be combinations of dimensions, right? But the key thing here is that TSNE needs to know what all the distances between all the observations are, because if it doesn't know, then it cannot reduce the dimensions to get you to the most salient visual representation of your data. So basically, yeah.
Yeah, so am I correct to understand that TSNE actually doesn't need coordinates, it needs pairwise distances?
Yes, it does. It does need coordinates. It needs the distances. Yeah.
So basically, let me try to put it in different words. So what you have is you have these attributes, and an attribute is sort of spread in a network. So like one is concentrated over here, the other one is concentrated over here. So these are distant attributes pairwise. Like, yeah, I don't know, sort of bass guitar and drums are far apart. Well, bass guitar and guitar are sort of close by, so they would have less distance. So basically what you're creating is a vector where each attribute is a line and each column is also an attribute, and then there's a distance. So you get a matrix of attributes connected to attributes, and then sort of like in the cell, there's the distance of this attribute to the other attribute. And then you run TSNE on this matrix, not on the network that you're originally looking at. Is that true?
Sort of. There is a slight difference. I mean, you can do that, but there is a difference between running TSNE assuming Euclidean distance on the matrix you just described, or telling TSNE this matrix that I'm giving you is not a matrix of attributes, is a matrix of already calculated distances. Now you have to find what the space is. So it's slightly different, these two things. But you can do both, actually.
So what are your, like you know, straightforward, like you give some kind of rectangular array to TSNE, right? Like something with a vector. And then you try to reduce the number of columns in essence, right? Or
yeah.
So what are the, like, and so for each attribute you have a line basically. And then the numbers in the columns are also sort of the distances of attribute Y to attribute X, basically. Is that true? Maybe
so the original object, and now I'm gonna specifically talk about the network example. The original object is a matrix where the columns are nodes of the network and the lines are the attributes of these nodes. So like each cell tells you, okay, these nodes for these attributes are this value, right?
Yeah.
So in my framework, what you're doing is that first you calculate all the pairwise distances between the rows of this matrix using the network. So now you get a square matrix where attributes are both nodes and column, and then you tell TSNE, okay, these are the distances between the observations. Now reduce the dimensions of this observation to 2.
Okay. Yeah, that's exactly what I meant. Okay, cool.
Okay, perfect. Great. Okay, so just let me give you some practical examples. So maybe things get a little bit more colored and more fun to look at when you actually see some examples. So as I said, this network is a network where each band is a node, and connection between bands are the same member playing in 2 different bands at different times, or also the same time. And now we can color this network with their attributes. We can say, okay, we can look at all the records that this band put out and say, okay, these many records were heavy metal records, right? And this is what you're seeing right now. So here we can use the darkness of the red here to say, okay, this is the share of the records that this band put out is heavy metal, or how much this band put out heavy metal records in general, right? And so you can see that there's a very specific part of the network here, right? So there's a very specific position in this network, because heavy metal, for instance, I don't know, I'm not a musical theorist, but it would probably require a specific set of skills and specific encoded genre requirements that people who play heavy metal will just share members with each other, or they will know each other because they play the same genre, so they may collaborate more likely, right? The same you can say, for instance, and this is actually much stronger true for hip hop. Hip hop is basically, if you take a record of hip hop, at the very least in Italy, I don't know if this is generally true, but you will take an artist A, they will put out records, and every single track of them will be in collaboration with some other hip hop artist. And this is true for all hip hop artists. So you end up with extremely densely connected cluster of hip hop artists that are basically all in each other's records, right? Then you can see another case of Neapolitan songs. Yes, it's a thing in Italian music. There's a specific tradition of specific encoded genre of Neapolitan songs, which also has its own part of the network. But now I gave you some example of things that where the connection between the network structure and the genres that these bands are putting out is relatively strong. But there are other cases that are kind of like more interesting to look at, right? So for instance, jazz. Jazz doesn't seem to really have a cluster. It seems to be like kind of like scattered around with no real logic, which is a fair position to have in the network. You can still cluster it. It will have weak relationship with other things, or a strong relationship with a thing that also scattered in the network in the same way, or in the same areas of the network. And there are also other cases like house music. I think I could have chosen a better example here, but where you can see that there is a cluster here, a cluster there, but they're actually in different parts of the network because there are different ways of intending the genre, right? I think the best example that I should have used, but I didn't, and I don't know why, is techno music, because I think techno music has some similarity with house, like it can be used in a commercial way to make people dance, but there is also a different current that uses techno music as a sort of experimental art. And so these two clusters, they're both labeled as techno, but you can clearly see in the network that are in different parts of the network. And I think this would have actually made a very much more interesting discussion if you actually could see the picture. And I don't know why I didn't do that. All right, so now I show you like 5 genres, right? I have hundreds. So can we do this systematically, right? Can we estimate these distances and find this cluster of genres systematically? And you can do that, and you can create this sort of hierarchical clustering, which I think also can be used to do a more sophisticated kind of analysis. Now I'm doing the trivial thing, right? I'm finding the groups. So I'm creating the boundaries because they make sense to me or to the algorithm that I implemented. But you can try to figure out how much this action really makes sense. Once you build a dendrogram, you can try to figure out how random this dendrogram is, right? So whether you should refuse to actually cut the dendrogram, you should refuse to draw the boundary, right? I didn't do this here because I didn't think about it, but I think it's an interesting thing to think about. But in any case, just to give you some example, like here now, the color on this heat map are the network similarities. So how far these specific genres are from each other when positioned on the network using this generalized Euclidean distance to estimate their similarity. And then you can build this structure by merging together the various clusters. And you can see that some of the clusters are very expected. So like we saw that something like heavy metal strongly correlated with the structure created this cluster, and you can see also for hip hop, for instance. So you do find these clusters in the network, but then you can find other things that are still interesting that you didn't expect by looking how the attributes was spread into the network. For instance, okay, so this is the Neapolitan song cluster that connects with other kind of war music things. But then here, for instance, you have jazz, right? And we saw that jazz didn't really cluster in the network. So there wasn't like this strong connection between, okay, I'm a band that put out jazz records, but then I don't share members with other bands that put out jazz records. But you can still see that the relationship between jazz and swing and twist and some other slightly more pop variation of it is still there. You can still find a cluster if you want to. And then there is also the kind of stuff that's in this like quadrant on the bottom right, which I will question instead the clustering a little bit more, because you can see here that the colors are distributed in such a way that bright means very similar and dark means not very similar. So in this quadrant on the bottom right, you can see that there tend to be darker colors, so the relationships here are probably more questionable. And probably you should think about whether you really want to do clusters or not. Maybe yes, maybe not. It still makes kind of sense. So you can see that there are different house variations that still can be considered clustered together. But the darkness of the colors make think that these things are weird, and so maybe they shouldn't be clustered together. Okay.
Have you? Can we ask you questions? So yeah. we got like 15 to 20 minutes to go, but like let me ask this question anyway. So there is a number of things in there. It's like one thing, if I look at this matrix, and I have this sort of kind of way of looking at matrices. It looks to me as if one could actually manually sort of flip the trees, the hierarchy, to make this almost a gradient. So what looks like three sort of like vertical and horizontal structures, it looks to me there is certain stuff that is very close related, and then you could actually sort it in a way that it is actually gradual. And then there is these weird things, like, for example, this trans house kind of cluster. If you go up, there is about 2/3 on the up, there's a bright spot which connects this sort of like techno house or house quadrant with some other patch of three really, really highlighted, yeah, exactly, this thing. So you could just sort that together, and then you would actually get a bright cluster of 9 by, or like something like 6 by 6, which is now not visible. So there's this weird thing, there's these off-diagonal sort of connections, which are quite interesting. It's not just the stuff on the diagonal, but also the connections off the diagonal that are quite interesting, because, we know like people like Frank Farian, who is Bonnie M, who did Schlager and house and disco. And so there's this kind of thing, like you may know him for one thing, but he also did this other thing. And functionally, once you realize it's actually the same thing, only one is sort of like, less sophisticated maybe. But so there's this kind of like really interesting sort of like pathway structure in music, where you have sort of similarities due to the instruments and stuff like that, which could be teased out of this matrix by further analysis. And there is a really interesting thing going on, I think, where, like, again, you can think about what are these clusters and genres? So in a sense, so this is a quite refreshing thing. Like, you know, I have one sport which I do since I'm 15 years old. I try to reorganize and resort my record collection every sort of like couple of months. And I force myself to do so, like, even if I like the order, to learn something new. And so one of the interesting things is not just what's the optimal sorting of this matrix, but what are the possible meaningful sortings of this matrix? And there are probably more than one, which is a really interesting kind of thing, which sort of puts the buckets into questions, isn't it?
Yeah, and I'm happy to say that in this specific case, I actually did it. So it's not in the slides because the way I made this plot, I had to wrestle a little bit with the technology here. It doesn't allow me to actually do different sorting. It just makes the clusters and say, okay, deal with it. That's what I did. But I did play with sorting this matrix in different ways, and I did make the gradient, and there is a gradient, I can guarantee you. And so there are millions of different ways of sorting this matrix. I actually played a little bit with, okay, what if I do PCA first? I reduce everything to one dimension, so I get a list of genres, and I use that list out of PCA to sort the rows and the columns of the matrix, and you can create those kind of gradients. So absolutely yes. And also there is also a slide that I dropped because it was extremely ugly. I had a very bad visual metaphor for this. But once you have the network, you can actually sort of like kind of like create these sort of maps where you can see exactly how, you know, different genres will kind of like make sense, how doing the both of the things together makes sense in different way, in different direction, because the network is by itself a very multidimensional kind of object. So you can see that, for instance, you can see kind of like this transition between rock, punk rock, and heavy metal, or like you get rock, indie rock, then you can get ska and reggae that then connects to hip hop. So you can go in whatever direction you want. And yeah, I explore a couple of these directions, which makes things very, very interesting indeed.
And one thing that strikes me here, like, could you confirm this, that the more sophistication is needed, the more flexible the musicians are? Like a jazz musician can play anything, while it seems like this, you know, sort of non-compatibility of the different versions of house could this be because there is really unskilled musicians where one has a TR-808 and the other one has a 303 and the other one has a 909, and they can really not play multiple instruments, and therefore there is a genre difference, which actually in fact is just, you know, basically being stuck with one instrument. While like it seems like the bright areas in this matrix are all, you know, if you have something like Schlager, twist, and jazz being close together, where it's like, no, wait, this is like really different branches of the record industry. But then you realize there is a connection, which is musicians basically being able to play all the instruments that are necessary. So do you think you could tease out something like that, that there is a sort of like, you know, like you could almost see a kind of gradient of musical sophistication here, isn't it?
I think so. I mean, I don't want to be too strong about this because I haven't thought about that, but I think there is something interesting that you can do that. And one thing that I did is, obviously, this is, as I said before, and as I repeated many times, this is a bipartite projection, right? Because the nodes are the bands and the edges are the artists shared by the band. But I also did the other side of the projection, which is a little bit harder to work with, where the nodes are the artists and they're connected because they play in the same band. And I cannot say anything about the genres, but I can tell you that when you calculate centrality in that network, systematically, the highest centrality when it comes to degree, closeness centrality, or between a centrality are drummers, which I don't know exactly what it means, but it probably means that it's very difficult in Italy to find a good drummer, and so you you have to share with another band. But yeah, so that there are, and this signal was very clear. I would say like, hey, but no matter how I sort this thing, they're all drummers, and not the same drummer, by the way. So yeah, there could be something interesting there.
Interesting. Okay.
I have
Yeah, Mike has a question.
Yeah, basically, I have a couple of questions. One of them is concerning this very dark red group, which is sort of top left out of from the this one. Basically, this seems to mean that they are even more different one from another than from the rest of the music combined. So why are they clustered into the same sort of dendra cluster in your dendrite clustering? Shouldn't they all be separate branches at the highest level?
So I think this is like a shortcoming on the visualization technique. Because if you look at the dendrogram, for instance, you can see that their mergings are pretty high. So they're not very similar to each other. But, you know, they're still like this group, the dark group is actually here, is like this thing here. So it's still more similar than other groups that I looked at, because they are not pairways, they're very dissimilar. But as a group, they're still a sort of a coherent group. And you can't see that in the visualization. In the visualization, you see this is dark, these are not related to each other. Pairwise, they are, but the group homogeneity,
Okay, and what is in there, by the way?
Yeah, so I think this may be the reason why I didn't use techno as the example before. I think this may be techno. So a bunch of different techno music. And the reason why it's so dark is that because it's probably one of the most experimental type of genres. So all the various subgenres are probably pretty different from each other.
I see. Interesting. Yeah, and the second question was completely technical. Can you tell a little bit about what is the source of this data set and how large is it and what time it covers?
So the source of the data set is a combination between Wikipedia and Discogs, which is Discogs is basically sort of like an IMDb of music. Geared towards people who want to purchase and sell various different records, rare records. So they have a lot of information about who played in the specific record, because they basically have metadata about everything that was in the booklets of the album. So sometimes, like, I use Wikipedia as an integration because for the most famous artists, it's a little bit more complete, because Discogs only records the information that is on the record itself, while Wikipedia say, okay, well, we know that these people have played together in this record, so we're going to put that information even if it's not in the credits, right? So because they're created in different ways. So like merging them, I think is a completeness argument. I don't know how good of an argument it is. We will see.
And why Italy?
The time span? Sorry?
Why Italy? Ask the time span first.
Let me address the temporal span. The temporal span is basically start from 1902 until 2023. Now, the 2020s are a little bit incomplete because things are getting out and not recorded yet. Like they're not in Discogs or in Wikipedia yet. And then obviously the records from very much back into the past are also incomplete because people didn't credit each other. There was different ways of crediting each other. The why Italy is, well, there are several reasons. One, I think, is because it's easier to make it self-contained, right? Because if I start saying I try to do the entirety of music, then it's just too big, and I need to find a way to figure out a way to slice the data. By the way, this is data that is collected semi-automatically, not completely automatically. So it's not that I download Discogs, which you can do. You can download the XML of Discogs. The entire thing is just a download button. It's a 80 gigabytes XML file. But Discogs has some things, like record some things that I find myself questionable. For instance, it will record who did the picture of the album. So like there is an image on the picture of the album, who made the photography, who decided the costumes of the people. Yes, I mean, I understand that these are people who know each other and they work each other and they collaborate on the record, but I wanted to remain on, they are more involved in the actual music production part. So if you were to analyze Discog automatically, it would be a little bit more difficult to get quality connections. So I decided to do this semi-automatically, which is like I process the data automatically and then I manually clean it. Which, yeah, it takes as much time as you think it takes. So that's another reason why I want it to be contained, because if I go on the full music industry, it's just too much work. And then that is the corollary of why Italy, there are other things that I could have done. I could have done Denmark, is more contained. But Italy, I'm very familiar with it because I know quite a lot about Italian music.
So how many records did you? So may I ask, like in Italy, like how many, like what kind of corpus are we talking about? Is this like 100,000 or 50,000 or?
Number of records, you know that I haven't bothered counting. I know that we are talking so far. What I cleaned is 60,000 artist to band connection. So we have 60,000. Okay. Yeah, edges between an artist and a band.
Interesting. Okay.
Yeah. The number of bands is around 1,000, and then the number of people actually in the data. Last time I looked at it, it was around 12,000, but probably significantly more now.
So does this mean that the number of bands in Italy is constrained to 1,000 bands being published on record or in CD, basically? So this is like it's a shockingly low number, isn't it?
Yeah, no. Let me correct you here. Those are the ones that I cleaned yet.
Okay.
Number one, and second, I also have decided. I can revisit this decision, but I have decided that I'm only including bands that have at least 2 records and they were active for more than 2 years.
Okay.
Because I want to avoid having those kind of like super groups that are like not really a band, but they just get together. I don't know what that will do with the network. I can revisit the decision. I have the data, it's not a problem. But so far, I'm focusing on bands that put at least out 2 records in at least 2 distinct years.
So you cut off like 2/3 of the data with degree 1, basically.
Pretty much. Okay. I mean, it's degree in a sense, it's not degree in another sense, but yeah, pretty much, yes.
So this is quite interesting as a hypothesis. Like I have this, like the more I look at historical data sets comprehensively across genres, the more I'm, in the 1990s, we were certainly overwhelmed by how much data there is. And now, like, I increasingly have the feeling that our universe was actually way more bounded than we may think. And there is a lot of possibility to explore because the universe was so bounded by industry and by institutions that were very powerful and sort of like led by a few people, basically. This is a really interesting thing. And the record industry is certainly one of these areas. I've sort of been familiar with this sort of shape with the American music industry, but I'm not surprised that the Italian one looks the same. So this is a really cool thing to learn at the end. So we used 2 hours. Thank you very much. This was great
already
discussion. Yes. So this was cool. This was a long 40 minutes, but we asked you a lot of questions in between. And I think there is a kind of thing to be taken home. This reminded me a lot of like our work together at Barabasi Lab, and which I enjoyed a lot. So there is something which I would like to sort of, advertise to people. There is a world beyond computer scientists and humanist experts encountering each other in an interdisciplinary way in digital humanities collaborations, which is people doing it in personal union, like multiple people with different expertises and different weights of expertises, but doing both things at the same time, being unafraid of the fact of saying, okay, I may not be a pure computer scientist and I may not be a pure art historian anymore, who knows what I am, but we can have really inspiring and sort of fruitful and, enthusing conversation. So thank you very much for these 2 hours. And you put up your last slide. I'm going to give you the last word. And you have something to say about era discovery in music, which is great. Yes, go ahead.
No, I mean, I just want to thank you for inviting me. This has been great. Also putting together this dendrogram looks awful because I did it on Friday in a rush because it's the last thing that I did. And I just wanted to say that the thing that I did with the genres, you can also do with time. So like a year is also node attributes, how many records this band put out in a specific year. You can do the hierarchical clustering. You need to do things slightly different, but then you can end up with something like this. You can try to build timelines and see where this timeline makes sense and when they don't, and try to build up different histories and see which ones are compelling.
Mm-hmm.
Thank you very much.
Thank you very much. Bye-bye.